This video is about junction field effect transistors, the sorts of transistors that are used inside electret microphones to act as the first stage of amplification. It corresponds to section 26.2 of the Applied Analog Electronics textbook. Let's take a look again at how the junction field effect transistor is used in the microphone. We have got a capacitor, variable capacitor here, that is the diaphragm and the electret, and it varies with the pressure, the air pressure on the microphone. One end of it is connected to the gate of a junction field effect transistor. The other end is connected to the source. And the only access we have is to the source and the drain of the junction field effect transistor. The gate is entirely contained within the can of the electret microphone and is not accessible to us. Okay, what exactly does a junction field effect transistor do? What's it look like? Well, here's a very crude cartoon of cross-section of a junction field effect transistor. We've got source and drain connected with a lightly doped, negatively doped region. The negatively doped region, it's got charge carriers, so it conducts. So we have source to drain conduction. The gate is a heavily doped P region. Because the P-N junction is a diode, what we get if the gate is not too positively biased is a depletion region between the P and the N, acting as an insulator that's separating the gate from the source and drain. So basically what this is a channel between the source and the drain that conducts unless the gate gets very positive. If the gate gets very positive, then we turn this thing into a diode, and the gate basically, you get current from the gate to both the source and the drain. If the gate goes very negative, the depletion region gets big. Because this is lightly N-doped, the depletion region is essentially all in the N semiconductor. And what happens is as the gate gets more and more negative, the depletion region gets bigger and bigger until eventually it completely pinches off that channel between the source and the drain. There's just nothing there but depletion region. And we get no conduction between the source and the drain. So when we've got 0 volts between the gate and the source, then we have a small depletion region. The source and drain are connected, and the transistor is basically on. If we take that a little bit positive, then we stop using it as a transistor and it becomes a diode. So we don't want to do that. If we take it a little bit negative, we modulate that depletion region and affect how good the connection is between the source and the drain. If we take the gate very negative, we pinch off the source and drain and just turn off the transistor entirely. Now, JFETs do sometimes get used near that pinch-off voltage, and so that voltage is reported on the data sheets. But the way we're going to be using it, we're not going to be doing that. Because if we go back to looking at our circuit here, we've got no way of putting a large positive or a large negative voltage on that gate. We have no access to the gate. How is it getting biased? How are we getting any DC voltage on there if all we've got is a capacitor? Well, we've got a diode here between the gate and the source, and the arrow there is basically pointing in the direction of the diode. So we've got, let's draw this. We've basically got a diode that goes from here to here, and also a diode that goes from here to here. And that's why the arrow here is drawn as going to the channel between the source and the drain, because it really connects to both of them. So if the source goes negative with respect to the gate, well, then that's going to turn this diode on, and it's going to conduct, and that's going to drain any excess positive charge that's on the gate. So the gate can't have a voltage above the source. I mean, anything above the source, and eventually it'll leak away. It also can't have anything much below the source. Now, the leakage in that direction is very much slower because it's a reverse bias diode, and a reverse bias diode has a very much lower leakage current than a forward bias diode would have for forward current. But there'd still be some small current. So this thing, because it's leaky, keeps the gate here at essentially the same voltage as the source. And why do I say the source and not the drain? I got the diodes to both. Well, remember that the drain is positive with respect to the source. So this diode is much more reverse biased than this diode. And so this diode is the one that you're going to get this thing going to 0 volts. At that point, this diode is still very strongly reverse biased and isn't going to give us any appreciable current. So we're going to be operating this thing with VGS very close to being 0 volts. Now those leakage currents around 0 volts, we do have a depletion region there, so it's a very, very high impedance. We're looking at gigaohms. So if we fluctuate the voltage here on the capacitor, the time constant for this capacitance and this very slow, very small leakage here is a very large time constant. So we're not going to see the signal here disappearing as a result of leakage through these diodes. We will, however, see that this will eventually get to 0 volts here. And so we can pretty much model the whole thing as if we just have 0 volts there. Now, what is it that this thing does? We said that the gate to source voltage is what's controlling the transistor. So we've got to worry about two things. One is, what is the drain to source voltage? Because the drain to source voltage is what's going to be providing us something to drive the current from the drain to the source. And it's got to be bigger than 0 here in order to get any current. And the current through the drain, that is our output. So we're going to make the drain to source voltage roughly constant. We're going to have the gate to source voltage fluctuating just a tiny bit around 0 volts. And we're going to see change in the current as a result of these tiny changes in voltage. So the parameter we're interested in is what's known as the transconductance. And that is the derivative of the current output with respect to the gate voltage. Okay, so the trans is because it's output with respect to input. It's through the device, not on the same side of the device. And the conductance is because it's current divided by voltage, inverse of resistance. Okay, so we're interested in this transconductance. In fact, we're interested in the entire sort of what is the current with respect to the drain to source voltage. That's basically all we can see from the outside. So let's take a look basically at what that is. If we plot drain current versus drain to source voltage. So now we're looking at just the things that we can measure here. Not the gate to source voltage, because that is not accessible to us. So if we look at this thing, well, when the drain to source voltage is 0, the current is 0. And this thing doesn't magically make current out of nowhere. It goes up initially linearly, and at some point it saturates. So this is the saturation current, and we have the saturation region here and the linear region here. Now I just lied to you, because when you do your experiments, this is what all the models say it does. But when you do your experiments, you'll see it's not really quite right. What the transistor really does, the linear region looks pretty good. But in the saturation region, it keeps going up. Not as fast as it went up in the linear region. And there are more complicated models of junction field effect transistors that include this effect, but they're pretty advanced and not very many people use them. Okay, so once we've done all these measurements, what good does it do us? Well, what we have to decide when we're using the microphone is what drain to source voltage are we going to put on the microphone. We have to bias the microphone in order to measure the current. How much bias voltage are we going to put on the microphone? And that'll tell us how much DC current we get, because remember, this voltage here is just the DC voltage. We put constant voltage across the microphone and we just measured what's the average current coming out of this thing as a DC thing, not paying any attention to the tiny fluctuations we get due to the tiny fluctuations in the gate to source voltage. Well, in fact, what do those tiny fluctuations do? Basically, if the gate to source voltage is a little bit more negative, then we're pinching off the transistor a little bit and we're going to get less current. And the models say it should do something like that. And if we put a higher gate to source voltage on there, it should let a little more current through, and the models say it does something like that. And again, what it really does, in the linear region, the models will look pretty good, but what it really does is sort of parallel the curve here. So what we're looking for is something where we've got the output current fluctuating pretty much just as a result of the gate to source voltage. Now, depending what circuit we're using, we may be holding the drain to source voltage constant, like if we're using a transimpedance amplifier to look at it, or we may have something where we have a load line where the as we change the current through the microphone, it'll also change the drain to source voltage. If we have a load line, we'd really like to be in the saturation region so that it doesn't really make much difference what the slope of that load line is, that we get the same change in current as a result of the change in gate to source voltage wherever we are on that line. So usually when people are using a microphone, they want to operate in the saturation region. If you're in the linear region, okay, things will work fine if you're looking at a transimpedance amplifier where you're holding a constant drain to source voltage. Things look a little bit messier if you're looking at something where you've got a load line, because now you're getting quite different operating characteristics, different responses of current to gate to source voltage in different points on the curve. So usually microphones are designed, the electret microphones are designed that the field effect transistor is somewhere in the saturation region. We can also take a look at the standard models that say what the saturation current should be, what the current in the linear region should be, and most importantly, what that says about the transconductance, essentially the gain of this transistor. And what we get is that in the linear region, the gain, and remember that's the derivative of the drain current with respect to the gate voltage, that's going to be roughly proportional to, I believe it's it's just VDS. So as we go up here, the sensitivity gets higher. So the higher the voltage, the more the sensitivity. In the saturation region, G is proportional to about the square root of that saturation current. So that in this region, the transimpedance gain is roughly constant, and it doesn't matter so much what the exact bias is on the drain to source voltage, because we get essentially the same gain from this transistor, so that we can put the same interpretation on the output current in terms of what does that mean for the input pressure on the microphone pretty much anywhere in this region. Of course, since that's based on a model that assumes the saturation current is constant, because it does go up somewhat with voltage, we do get some change as we move out here, and I believe it actually gets slightly more sensitive as we increase the drain to source voltage rather than remaining constant, the way the simple models say. What that means when you're using your microphone is that you need to put a voltage across the microphone enough to get a substantial current, and that's going to take you into the saturation region somewhere. So you have to make sure you've got enough bias voltage in your microphone to get you into saturation. And that's probably all you really need to know about the junction field effect transistors for what you're going to be doing with them in this class, because you're not going to be designing with the field effect transistor itself, just with the microphone that incorporates the field effect transistor.